Dear colleagues, let us continue. Let me introduce Paolo Villaresi from University of Padova in Italy. Quantum Communications in Space. Very intriguing title. Please, Paolo.
Good morning, good afternoon, everyone around the world. It's my great pleasure to be here with you today. I will discuss on this fascinating topics, quantum communication in space. There is something that intrigued us a lot, and we essentially started it when it was an empty field, and nowadays it's instead very active and full of ideas and projects. Okay, I'm from Padova, Padova University, which is celebrating the 8th centenary this year. In particular, we have a quantum technology research center. I have the honor and the pleasure of being the director. Putting together expertise from scientists of different backgrounds. There are chemists, mathematicians, physicists, and engineers. And with this, we try to tackle problems that are essentially larger than the expertise of just a single discipline. Okay, so just one remark: quantum communication are the most fundamental level communicating system because they are sharing elementary states. So you are sharing states at the quantum level between systems. Okay, so what you achieve is actually a connection that is at the deepest level. Okay. So from the point of view, the physical point of view, this is of course interesting, and the main perspective is to be able to extract meaningful information from a system and be able to convey somewhere else, to measure, to make it to interact, to participate to a computing, okay, with another system. Okay, so physically you have these real problems, okay, but there are many other things that you can do with quantum communication because of these quantum technology things. So these are essentially the marriage between the quantum mechanics and theory of information. So instead of having just the problem of understanding things or explain behavior, you actually have the purpose of doing protocols. The protocols, the ideas, the problems of the theory of information, like communicate, compute, measure, okay, are essentially empowered by the tool, the carriers of quantum mechanics. Okay, so you're using quantum tools for doing things that are of interest for information theory. Okay, so in this sense, it represents a new avenue for physics as well. Okay, so the quantum communication is the art of sharing quantum state. Okay, as we say, for that we need using, say, the carriers, and light, of course, is the most powerful carriers because it can travel across the universe. Okay, more in detail, you are looking at the quantum state. So you have to pick a degree of freedom of light, be able to encode using an alphabet the protocol that you would like to use, and then to essentially make measurements. Okay, measurement can be simple. You have in the slide a photograph of a device that is measuring qubits coming from the space. Okay, you have an interest port connected with the telescope, two output ports, and you put a single photon detector out of it. What you get are clicks. The clicks are correlated to a particular output, to a particular measurement, and this is all you need. Okay. A protocol, a well-known protocol, for instance, is the BB84 for sharing keys to remote location. There are many applications out of this, and the idea is to leverage on principle of quantum mechanics, as we were saying in the introduction. Okay, so you're using superposition principle, quantum measurements, and in this particular case, in the prepare and measure, you create single photon state or quasi single photon state, picking at random one or two bases between two of mutually unbiased bases with one bit, with classical bit. With the second classical bit, you choose which vector you have to pick, and then you select a particular polarization or whatever degree of freedom you are using state for the photon, you are sending that photon, and at the receiver, Alice and Bob are usually the main characters of the story. Bob, the receiver, is also picking a random base, and along that base does a quantum measurement. Okay, the result may be connected if the two bases coincide or not. And out of this, you create a protocol that essentially creates a string correlated from one side to the other. Then there are two more steps: the error correction, which is a classical procedure to clear up from problems in the communication or dark counts or background photons received by the system, as well as the last very important step, which is the private simplification, where the information obtained in the error correction, so the amount of error that in that particular transmission has been found, is used as a parameter to shorter the two strings, okay, of a quantity that is related to the QBER and gives you at the end something that is essentially clean from shared information with the third parties. Okay, so it's a pair of strings equal and known only to the two legitimate transmitters. Okay, these things, for instance, make an example from something that started as a scientific research area to application. Europe is investing on this technology for the quantum communication infrastructure for several reasons. There is, for instance, a testbed project spanning over several countries aiming to demonstrate these things. Okay, as I say, degree of freedom. You need degree of freedom for light. You can have polarization, temporal modes. For short distance, we also have used the orbital angular momentum, but they don't travel the long distance to the hole. Sending from space, you ask the question, what's the best scenario? From space to ground, from ground to space? Well, as you have the turbulence, it's affecting, of course, Andrew, you know very well this, the wavefront close to the ground. Of course, the downlink is preferable if it's possible, because you're actually traveling in the vacuum for a long step, and then you are marred by the turbulence degradation only at the end. Okay. In this area, as I said, we started in 2002, sorry, the first experiment started in 2003, for essentially showing that you can couple, you can exchange a single quantum from an orbiting simulated source to ground. It took 5 years for us to get that spike at the center where you actually expect the photon to come, okay? And then we picked 1 degree of freedom. The most obvious selection was the polarization to start encoding. So taking this mutually unbiased basis in a Matera telescope, one of the station of the Italian Space Agency, with a 1.5 meter telescope devoted to laser ranging that we transformed into a quantum communication hub. So you see in the graph, the first QBER measurement ever done in space in 2014. We picked the HV left and right state, and we have it through the right output port in the quantum measurement setup. It was checked that it was a single photon level at the source, so in the satellite, okay. And of course, the laser ranging allowed us to ensure that the radar equation allowed it to match this. This was indeed the highlight of the year in 2015. The point then is you can choose different degree of freedom. For instance, on temporal modes. With that, you can address a fundamental problem that is checking the superposition principle, the visibility when you have essentially interference over space channel, which is again something new to test. And we realized an experimental scheme essentially by taking a time beam, as it's called. So you have a wave function that has 2 lobes, and the phase between the two, okay, is the one that you are looking, okay, that allows you to make an experiment. In the graph here, you see essentially the possibility of going through a short and a long path to the space, go to the satellite, being reflected, coming back, and through the same interferometer, you may have essentially the return that on a port where you have the detector gives you 3 peaks. The first and the last are the one corresponding to just one amplitude. So the chance that the photon has taken the short path going out, the short path getting in, so it's coming earlier, or vice versa, has taken the long path going out, the long path coming back, and so it comes after everything. But in the between, you have essentially the interference of 2 alternatives, the photon that has chosen the path short coming out and long coming back, and vice versa, longer coming, going to space and short coming back. And these 2 interferes, okay? You can essentially model this with the kinematic phase, this feed that you see in the state, and essentially this phase depends on the actual instantaneous velocity of the satellite with respect to ground. The reason why is that the satellite is approaching or going away from ground station, and in this sense, it's moving, for instance, while approaching towards the ground station. So the, say, point in space in which the pulse is reflected back when the second part of the wave function approaches the satellite is slightly different with respect to the first one. Okay, so at the end you have that this difference that we call it the kinematic phase is making the probability of getting a click at the central lobe to essentially change from 1 to 0 many times, and that's the red curve that you see oscillating there. So we did the experiment for a number of satellites. We actually see the visibility attesting the validity of this model for superposition of these 2 states, and this was also a confirmation of the possible use of the temporal modes in the space channel. Of course, you have to do the calculation well, doing the booster in special relativity to satellite and back. Okay, the effect of general relativity are minor, so we have no sensitivity to observe them, but we clearly see the effect of special relativity. Going on, we addressed another fundamental issue, that is the wave particle behavior, leveraging on these 2 degrees of freedom. So as the 2 giants here have discussed on the essentially the quantum behavior that allows you to decide which type of measurement without to projector apply to your state at any time, even a very last time before the measurement, that was brought to an extreme, let's say, by John Wheeler in his well-known delay choice Gedanken experiment that translated into space channels. Means that we can have a photon that is traveling from the satellite to ground, and we decide only at the last moment whether to measure its path, so which way he has chosen, or the phase, the polarization phase, so essentially the wave-like behavior or the particle-like behavior. Okay, this was indeed possible by combining the 2 degrees of freedom that we demonstrated separately earlier. And so by combining this with the quantum random number generator that activate once the satellite essentially reflected after satellite reflected the pulse, we have essentially a random decision that tells which type of measurement to apply. Okay, so the results are here. If you are measuring the interference, you have essentially a recombination of the 2 paths. So you have a single peak, and the height of the peak depends on the essentially value of the kinematic phase. So it oscillates in the graph that's here with interference. Instead, if you separate the 2 paths, you have essentially a pulse arriving earlier or later according to the type, say, which path the photon has chosen in the interferometer. And the interpretation of the result is such that essentially, if you look at the particle-like behavior, this is something that has a visibility of 95%, that leaves only 5% to the, say, wave-like behavior, And since this was about 40%, it was clearly incompatible with the point of view for which you have an entity that can be a particle or wave, but can be both at the same time. While quantum mechanics is predicting both, and we actually demonstrated it in space for the first time as well. In terms of application, this is, of course, a protocol that may be used for in the perspective we have seen. Okay, we introduced say devices to be used in space or on ground. One is the IPONAC, that is essentially a PONAC for doing the polarization measurement. That is very robust and stable. It has record low performance in being silent in the liquid bit generator, being awarded by an international prize this year. Other tools are, for instance, the synchronization made on the qubit stream themselves, so no need for other type of lasers. So we tested this on the ground, and just to show you that these things are now at the level of application together with the random number. You also need the random number, very genuine, that can be generated with quantum protocols. We have a number of results and ideas with a pattern on this. They can be mounted on chip, and with the combination of all this, we have, for instance, links in Padova that works on free space, on fiber, on both intermodal quantum key distribution, for instance, and even a spin-off that is delivering the boxes for doing this. Okay, so in terms of ground stations, we have, of course, the access to the great telescope in Matera, Vasi, but also that is very big and, of course, expensive. But we are also aiming to demonstrate the feasibility of quantum key distribution from space with a smaller telescope like the one you see on the bottom right of on the picture here, okay, which is in Padua. So this is a brief summary of our achievement from 2003 to this year. As I say, it still remains a very interesting pathway to new science, combining different degree of freedom. This is the message that we like to leave, and essentially something open to collaboration internationally with Ukraine, and we are very looking forward for this. Okay. With this, I would like to leave with the photo of people in our group, in particular the youngsters that actually are working in the lab with enthusiasm and passion for research. Thank you.
Thank you very much, Paolo, for the very interesting talk. It's very inspiring what you have with photons to do. The talk is open. Questions? Andrei Semenov, please.
Yeah, thank you. Paolo, first of all, thank you for your nice talk. And my question is, in your just pre-last slide, I believe, maybe pre-last or something like this, maybe, yeah, this one, you mentioned about fundamental experiments on relativistic effects in quantum key distributions. Could you please comment a little bit more about this interesting topic? Is it feasible experiments today, or how?
The point is, the quantum key distribution is an application, and you will like to have it the most robust as possible. Okay, so for that you try to choose the degree of freedom and the type of measurements that are the least sensitive for these things. So, for instance, the phase that I've shown before, it's a very sensitive parameter, so it's good for going along the fundamental research. It has also quite good, say, properties for fiber transmission. Okay, but in space is batch varying. So you would like to use more the stable part, so maybe polarization in space, and in that case, it's much less sensitive of special relativity, for instance, while the phase is much more. So you tend to separate the fundamental physics part, okay, and the degree of freedom most suitable for that, okay, and the application with the most robust choices, okay.
Okay.
Usually you do, I mean, also me choose a selection for degree of freedom was on polarization from space. We studied also CV coding from space. As you know, this is very sensitive to losses in this case. And as you know, from space, we have to take into account larger losses than you have on ground in general. Okay, also fluctuating losses, which is a very interesting point. And these are essentially posing some issue on the CV. Our approach, coming from also the previous experiment on ground turbulence mitigation experiments, was again to chop the time axis and do local tests on the characteristic whether or not they are allowing you to create a key, a positive key in the field. Can send you the reference if you like.
Oh, thank you very much. Thank you. And if it's possible, one short second question.
Yes, please.
About alternative theories and field theory in the same slide.
Beg your pardon, could you
Is
repeat?
something about quantum gravity testing in space, or?
As I said, the general relativity effect were too small to be addressed with interference in the experiment that we did. Okay, and of course now we are thinking on how to say put in evidence that these type of effects, which are essentially 6 orders of magnitude smaller, even considering that still you have the special relativity effect on it. So you have the Doppler and many other things. So the scheme for addressing the general relativity effects have to essentially clear the big, I mean, 1,000,000 times larger effect in special relativity, and then address the other for gravity. Okay, we have a couple of papers on that as well, and share it with you if you like.
Thank you very much. It's very impressive.
It's my pleasure. It's my pleasure.
Thank you.
Next
Okay,
question.
all the
from
best.
Next question from the chat from Evgen Britavsky. What sources of single photons were used in your experiments?
These are attenuated laser that are running in the regime of a few tens of picoseconds, filtered out spectrally. So it depends on the particular scenario, but we started from either mode locking lasers and we chop down the intensity, or we trim in order to have a single photon from the satellite, or we start from semiconductor lasers. We actually, according to the type of experiment, they may have different solutions. Okay, so attenuated coherence or chopped laser or mode locking laser. There are, as you may see, there is a multiple way of approaching the problems, and yeah, these tools are useful because they suit better in one case or the other.
Thanks. Next, Alexander Kardyuk, please, short question.
Okay, just wanted to ask about this kinematic phase modulation. So first, just to understand how large is this lag in meters, and so of splitted photons, and actually how you could distinguish this phase modulation which comes from traveling them in space from this modulation, which additional modulation which it gets in this lag.
Very good question. And indeed, it's an interesting feature because true is that you have a satellite that is running like hell, 7 kilometers per second, is approaching you and going away, okay? And the technique of working with this phase is very subtle in the sense that since you are probing the satellite with a state that has these two lobes, okay, this technically has realized with the unbalanced interferometer with just 1 meter of unbalance. So it's about 3 nanoseconds of distance between the two, okay? So one say, what can you do with this 3 nanoseconds? But wait, you have something that is traveling like hell. So at the speed of 7 kilometers per second, even 3 nanometers correspond to a few microns, okay? So the satellite, the displays of a few microns while it's approaching towards the telescope or going away. And you say a few micron, no, a few microns are a lot if you are looking at the light interference, because there are several wavelengths that are involved into that. And indeed, if you look at the dynamic of the kinematic phase along a satellite passage, so essentially looking at the velocity that goes from minus 7 kilometers per second to plus 7 kilometers per second, okay, you have essentially a 400 pi of phase change. So you actually go along a very large number of oscillations. This was the red curve we have shown. And these are because indeed you are meeting the condition for constructive interference, destructive interference, and back and forth many times. And it's a very subtle issue that can even be envisaged as a metrology for speed, instantaneous speed, because it's done essentially in 3 nanoseconds.
Okay, thank you.
It's my pleasure. Thank you. I'm glad to share with you the slide, and there are all references in it as we wish. And I'd be glad to further discuss for supply.
Very nice. Thank you very much, Paolo.
It's my pleasure. All the best. All the best from Padova. Bye-bye.